Hey everyone, my name's David, and today I'm going to be talking a little bit more about Plasma. Plasma is super cool. You can use it for a lot of things, and hopefully you'll learn a little bit more through this talk. So here goes. I was actually practicing the clicker usage, and it did work. I think so. Okay, well, Plasma's, like I can do this ad hoc, but I'd prefer slides. Oh, awesome. So today I'm going to kind of divide my talk into three segments. One, why it matters, scaling and Plasma in particular. Two, what's happening right now. Carl covered some of it earlier. I'm just going to give like a few more details about it. And then three, big picture, the Plasma vision. So here goes. So why it matters. Scaling, it's the name of the game. It's what everyone is talking about. There was just an event in Barcelona about scaling. So it's kind of important. But why is it so important? Well, Ethereum's wonderful, but in its current state, it's single-threaded. And this is fine for one computer. It's even fine for two computers that are running all the transactions. But as soon as you get to around 20,000 computers trying to process basically the entire transaction throughput of the Ethereum network, it gets pretty crazy. And now that people are actually excited about using blockchains and using Ethereum, the infrastructure has to catch up, and that's why there are so many emerging scaling solutions on the horizon. Plasma is one of these scaling solutions. What makes Plasma so special is that you're able to make another blockchain which derives its security from a root chain. So in the case of what we're building at Omise Go, the child chain will derive its security from Ethereum, which is super awesome because blockchains currently derive their security from economic incentives. So if you're just starting a side chain, when it's just starting out, it probably won't be worth that much. So it'll have a relatively low cost of attack. But with Plasma, you can get increased transaction throughput with a child chain while basically building it off of the economic security of Ethereum, which it's well proven, it's in production, and it's worth billions of dollars. So you get a lot more economic security from it. So how does this all work? Scaling through compaction. So this is a fairly simple example here. We have a UTXO set, and that makes up the state of the child chain. And then we use cryptography to basically take that state and then squish it down into a compact form. I call it a restorable state. And then we put that restorable state onto Ethereum. And Ethereum is kind of the final arbiter. Ethereum keeps track of that state. But how do we recover this recoverable state? Well, we use cryptography. So we compressed it using cryptography, and then to get it back, a user or anyone really could basically create a cryptographic proof that basically at a given time this state was a certain way. In this example, at a given time, Alice owned a particular UTXO. And then the user basically specifies Alice's UTXO, puts in a proof, and then Ethereum processes that and checks that everything is valid. And then boom, you have Alice's UTXO as the output without having to store it directly. Ooh, cool. Projector's still on. So how does this actually work in the case of a UTXO set? Well, right now we're using Merkle proofs. Some of you have probably heard about Merkles. They're super cool. A lot of things blockchain related use them. Ethereum uses them. Yeah, they're awesome. And basically, what they're best at is proofs of inclusion. So basically proving that at a given time something was part of a given set. So in this example here, we have a UTXO set. We hash it down, so basically turning each UTXO into a 32-byte hash, because that's easier to work with. And then we start hashing things together until we get a root of the UTXO set. And then we store that root on Ethereum. And that is basically the restorable state. And through that, we can prove that Alice had ownership of one of these UTXOs at a given time. How do we do that? Oh. Well, we basically create the path of hashes leading up to the root. So Alice would submit a UTXO, but then she'd also submit the necessary hashes to recreate the root of the Merkle tree. And then through that, she basically has proof that she owned it at a given time, which is super cool because it's significantly more easy to just store a root on Ethereum than the entire UTXO set. Ooh, shit. Boom. Now I'm going to talk about some stuff that's happening now with Plasma. Boom. So Plasma MVP, the first spec written up by Vitalik, is basically a UTXO payments blockchain, significantly similar in terms of functionality to Bitcoin. And that's kind of the first stage of pushing Plasma from a white paper into something actually implementable. And right now, there are multiple teams kind of working off that and then iterating upon that further. But how does it actually work? Well, we have first UTXOs, unspent transaction outputs. And basically, they need to specify an owner and an amount. So who has the money and how much money do they have? But we kind of get an issue. When we're using UTXOs to track who owns what, one person can have multiple UTXOs. They could even have 1,000 UTXOs. And so in terms of kind of maneuvering these around, it's quite difficult because the way Plasma MVP works is if anything goes wrong, everyone has to exit within a given amount of time. And so if one user has 1,000 UTXOs, that means they would have to perform 1,000 exit transactions on Ethereum. And we don't want anyone to have to do that. So we use account simulation. And what account simulation is basically doing 2 UTXO transactions to simulate accounts. So in this example, Alice has 100, Bob has 100. Then Alice sends a transaction, creates a transaction, giving herself at 95, and then giving Bob a UTXO of 5. And then Bob still has the UTXO of 100. So as you could imagine, if we stopped at this stage, Bob now has 2 UTXOs. This could basically, he could basically accumulate more and more UTXOs, and eventually exiting would become very difficult and expensive. So to prevent this, on the child chain, what we have Bob do is we have Bob do one more transaction, which basically just nets his 2 UTXOs into one. And that basically makes it so that for most of the time, each user of the child chain will have all of their value in one UTXO, which for using, it can be thought of as an account, which is super cool. But how does Plasma MVP actually work? So we start with basically a contract on Ethereum that is securing the child chain. And when users want to start using the child chain, they deposit value from Ethereum, from like their token smart contract or Ether. They deposit that value into the Plasma smart contract on Ethereum. And those funds are basically locked in to the Plasma smart contract and will only be, and they basically come out again on the Plasma side of things. And then you basically, when a user exits, they regain access to their funds. In the case of Plasma MVP, a user deposits funds, and for simplicity's sake, this actually creates a new block of the child chain on the Plasma smart contract on Ethereum. And this is super cool because before we had to deal with kind of two types of withdraws. One where a deposit basically was made, but it never showed up on the child chain. And then you had to basically prove that you made a deposit. Whereas now, because the deposit shows up in a child chain block instantly on Ethereum, all users have to do is go through the normal withdraw process. So for both deposit cancels and normal exits, there's one process, which just limits attack vectors and makes things significantly simpler. Boom. So how do these transactions actually look? So you have inputs, which are basically referencing the positions of previously created UTXOs. And these inputs, they need to basically be referenced. You reference the transaction position where the UTXO was created. And you also need the signature from the owner of that input, because we only want the owner of a given UTXO to be able to spend it. And then you have outputs, which are the new UTXOs. And then you have the fee. So this fee, much like with Ethereum's gas, basically pays the consensus mechanism for providing the utility, and also prevents DDoSes. Because even though we'll get a large amount of scaling without charging people fees, they could basically overrun the child chain with a bunch of spammy transactions, and that would be basically make it useless. But we can do more. So basically, with child chains and with Plasma MVP transactions, we need confirmations. Because right now, there's a situation where, and I'll get to why we need confirmations in a bit, but basically, there's a situation where someone can send a transaction, the operator can withhold it, and there's basically no way to prove whether someone has actually double spent it and it's been included in the child chain, or if the operator is just being bad. But with Plasma and child chain transactions, we want to support more than ETH, and this is really simple with kind of the UTXO model. We just add one more field, and that's currencies, and all of a sudden you can support ETH and ERC20s, and eventually pretty much any currency down the road. And the key kind of security principle of Plasma MVP is that if anything goes wrong, everyone has to exit. So if you're validating the child chain and you see an invalid block, or if the block, basically the consensus mechanism block, like the child chain operator, suddenly starts withholding blocks, you assume that something bad has happened, and you have to basically all in exit on Ethereum to get your funds back within a given amount of time. So what does this actually look like? On Ethereum, we have a priority queue, so that basically keeps track of the order of exits. So basically, if you're watching the child chain and you notice something sketchy is going on, or if there's block withholding, you basically exit your UTXO, and if you do it within 7 days, you're basically guaranteed to have your UTXOs successfully exit before an invalid UTXO, which has been created later. So this works super well. It's a little bit annoying because exits are processed in the priority queue. You have to pay a significant amount of attention to the child chain to constantly verify it. But yeah, it works. But it's basically a fractional reserve on the Ethereum root chain, which is not optimal in the sense that an operator, if left unchecked, can then withdraw and basically create money out of thin air. Awesome. So here's where we're at now. So right now with Plasma MVP, someone deposits funds, they get their UTXO back out on the child chain, they can kind of play around with UTXOs, juggle them around a bit, and trade them to people, do kind of swaps with them, and then once they're ready, or if anything goes wrong, they go through a withdrawal. Now for a story. So I just want to emphasize why confirmations are so important, because when I first was kind of looking into Plasma, I kind of basically, because confirmations are a pain from a user experience perspective, I kind of kept trying to wiggle my way out of them. But at least for right now, confirmations provide a super valuable service and play an important role. So in this story, we have Alice, Bob, and Hades. And Alice and Bob are just normal users, and Hades is the child chain operator. So everything's going normally. Alice is on the child chain, and she sends a transaction to Bob, transferring Bob X amount of money. But the Hades, the operator, is basically a bad actor, so he's trying to steal everyone on the child chain's money. So what he does is he takes Alice's transaction to Bob and he withholds it, so he doesn't include it in the child chain. Then he creates an invalid transaction, includes it in the child chain. Then he exits that, and then he includes Alice's transaction to Bob. But he withholds that transaction, withholds that block. So Alice really has no way to even know if her transaction has ever been included in the child chain. So here's what happens. Basically, the operator is bad, but because the operator is withholding, we can't prove it. So Alice realizes something bad is going on, tries to exit, but once she exits, the operator can basically submit proof of a double spend, because he did include Alice's transaction. He just included it later and withheld the block. So Alice has no way to exit. And then if Bob sees the successful challenge and uses that information to try to exit himself, because now he's the rightful owner of the given output that Alice created for him, he can't exit either, because his transaction was created after, or was basically the transaction that created his unspent output was included after Hades' invalid transaction. So if you remember the priority queue, what would happen is Hades' invalid transaction would clear the Plasma smart contract on Ethereum before Bob's exit. And basically what happens here is that Hades ends up getting away with everyone's money, but neither party's exits who should have access to the money will get to basically occur successfully. With confirmations, what we're basically able to do is Alice only gives up custody of her funds once she is able to see that her transaction has been safely included in the Ethereum Plasma smart contract, and when she has access to the given block where it was included, so she can basically validate that everything up to that point is basically valid transactions, no creating money out of thin air. But Pcash, this is what everyone's talking about, and there's basically significant progress in this area. Non-fungible tokens blockchains are super cool, because if you remember the problem I was talking about where when we have a fractional reserve, basically a child chain's consensus mechanism can create money out of thin air if the users aren't paying enough attention. Well, we don't have this issue with non-fungible token blockchains, because every asset and its unique ID is stored on the Plasma smart contract on Ethereum. So what this means is that an operator can't just create a new object and withdraw it, which is super cool. But the operator can still basically try to steal an object by withdrawing something that doesn't currently belong to them in the most recent state of the Plasma child chain. So we still need to watch it. But instead of checking the entire state of a child chain, Alice only has to check her piece of the child chain. So she's checking her basically Merkle proofs of exclusion that prove that her unique objects that she owns haven't been accessed. And she doesn't really need to care about everything else, which is super awesome because as we start to get bigger child chains and more transactions per second, if each user can remain safe by only checking a small piece of data, basically what they care about, it allows for a lot more scalability. So yeah, and when Hades comes in and tries to steal Alice's transaction, even with the small amount of state, she still has enough information and enough power to basically prove that no, she is the most recent owner by submitting a later transaction that proves that, hey, no, at one point Hades owned this, but actually he basically did a transaction transferring ownership to me, and Hades is not able to steal her money, and this has been achieved with no confirmations, which is awesome. So how? Basically, if Hades tried to create something that wasn't valid, it'd be checked on Ethereum, and it wouldn't go through. Because we have a clear record of what's happening and the value of all the assets that are stored on the child chain, and nothing can be created. When Hades tries to submit a fraudulent value, it's just stopped right away, and we don't have to worry about a new kind of asset being created on Ethereum. So, big picture. The Plasma white paper promised multiple layers of child chains and them all talking to each other, them verifying each other, basically varying app-specific child chains depending on the needs of an application, and basically a bunch of cool things. And that's currently being worked on. There are people working on kind of how Plasma can be used to do computation, how we can use account models with Plasma, how we can eliminate confirmations, how we can basically do other stuff besides payments. And yeah, that's going forward. It's a process. Eventually, general state transitions will be possible with Plasma. And yeah, when that day comes, it'll really open the floodgates, because then someone can basically take a Solidity smart contract, and without having to think about how to basically secure a specific Plasma chain that has their given functionality, they'll just be able to deploy a Solidity smart contract on a Plasma chain, and it'll be super smooth with low transaction fees. So yeah, Plasma chains. And how will this look, though? And the best example I've heard about how these Plasma chains will kind of interact with one another and how security will be derived is through courts. And so we start with the courts of first instance. This is the lowest level court. And so these child chains will basically have really quick transaction throughput, and the transaction fees will be the lowest because they're basically the furthest removed from Ethereum where security is derived. So if anything goes wrong, it will take more arbitration, and there's less economic guarantees for the lower down chains. And then we'll have the Court of Appeals, where the courts of first instance are secured by the Court of Appeals. So if anything goes wrong on these, it makes the most sense for a user to kind of say, hey, no, submit a fraud proof. This is what actually happened to the Court of Appeals, because going one level above will be significantly cheaper than just jumping to Ethereum. And then finally, we have the Supreme Court. So in this case, this would be Ethereum, and this is basically the law of the land. If everything goes wrong on child chains, you basically have to resort to using the root chain to settle all disputes and make sure everything kind of turns out the way it's supposed to. The downside to this is as Ethereum grows in popularity and the mainnet receives more and more uses, gas costs will probably rise. And with that, it'll be more expensive to settle stuff on Ethereum. So the goal is for that to happen as infrequently as possible. Boom. So as you see here, we have the different layers of basically blockchains that are talking to each other, talking to the root chain, and boom. Yeah, so kind of going forward, talk about what matters. I'm going to echo what Adrian said. Build the scaling solutions. Don't just wait for them to come to you. Yeah, there's a bunch of cool projects who are actively searching for people like all of you to contribute, to add value, to use your creative and beautiful minds to contribute wonderful ideas. Do research. So yeah, once you have wonderful ideas, kind of pick them apart, talk to people who are smarter than you or who have more experience, and then yeah, kind of meld your creative ideas into solid specifications, and yeah, build them. Boom, boom. Build your own plasma. Oh, yeah, sorry. Yeah. Build your own plasma chains, app-specific use cases. Plasma can change the world.
I have a quick question. In your diagram, you had a payment where you had 2 inputs, 2 outputs, a fee, 2 confirmations, and a currency.
Yeah.
Is that fee just a third output?
Yeah, it would essentially be a third output. Yes.
And so I'm a little confused. If that's a third output, why? I mean, you sort of answered it with saying that you account for every unit, every atomic unit of account on the parent chain. But in the other example, why couldn't you do that same thing? Why could the operator create a UTXO like how could an operator withdraw as a normal user a UTXO that wasn't put in from a normal user, right?
How could the operator withdraw a given UTXO like an invalid UTXO? Is that what you're asking? Or?
Yeah, like how can they create value inside the chain as the operator if the value is only valid because if the parent chain is still the source of truth for currencies?
So basically, the parent chain is only accepting root the TX list roots from the consensus mechanism. So basically it doesn't do any validation when blocks are submitted. So the operator can basically make a transaction saying whatever they want. They could even basically pretend that a deposit was received that was never received.
Ah, right. Okay, I get it. So because the Merkle root doesn't actually contain the full transaction log, just the state of the UTXOs.
Or it contains the full transaction log, but basically the operator can withhold like an invalid block that either has double spends where they're getting money twice, or basically any situation where the operator has more money where they're supposed to, whether that's through double spending, them pretending that Ethereum received a deposit to the child chain to them that never happened. Yeah, basically a bunch of situations. So that, cool. Oh, yeah, you. That's awesome.
Hello. So my question is whether you're planning to include some kind of programmability into Plasma, at least to the extent that Bitcoin is programmable. Because, for example, one of the useful things that you can do with UTXO blockchains is atomic swaps. Like you can swap things between different UTXO chains. And if you just used Bitcoin's script, that would already allow for it. So actually, why are you reinventing the wheel? Why aren't you just using Bitcoin's UTXO format?
Well, so Bitcoin script is wonderful, but Bitcoin, or not wonderful, but it does give you added functionality. And but it's significantly simpler with Bitcoin in the sense that Bitcoin is its own blockchain, so it relies on its own consensus mechanism, and there's not another chain that has to track each of those state transitions. Whereas with Plasma, you're basically tracking every state transition on Ethereum. So if something bad happens on the child chain, you're basically able to settle that on Ethereum. So I wouldn't say it's reinventing the wheel to not include it right away. I would say that the majority of Bitcoin scripting functionality could be included right now on a Plasma chain, but it would look more like specific functionality, like say multi-sig functionality, as opposed to having like the scripting opcodes that people can put together. Yeah.
So let's say like in this Plasma Cache example, the user only keeps or remember his own transactions when we have, like a super big operator. And so then the user wants to exit, and operator like blocks him, and the user tries to do reconciliation on the mainnet, but he doesn't have all the transactions, yes, because probably he depends on his inputs from other users, and he doesn't have this parts. So how he can reconcile when the operator doesn't agree or doesn't share that part?
So user only should count and give an asset as received when they're able to exit with it. So if I give you an asset, but in between the operator starts withholding, you never have custody of that asset. You never would exit that. I would be responsible for exiting that until you're able to basically, until you see my transaction to you included in the child chain and then included in the root, and then you would have enough information to exit. Does that?
But then I will need to remember all the side chain.
What?
I will need to remember all the side chain.
No, you just need to remember, so basically once my transaction to you is included in the child chain, you basically will receive, you basically only need to know the proofs that prove that you own a given asset. You don't need to validate the entire child chain. You just need to receive proofs of the transaction, proof of the transaction where I'm transferring ownership of a given asset to you.
We can talk about it later.
Okay. Oh. Do you want to do one more?
So the security assumption is that I have to watch the chain and exit, right? And then we already started talking about multisig and like advanced scripting, and maybe we get general state computations going or not. But I would just like to get your opinion on how to handle like multisigs or DAO-like smart contracts, or even the plasma bridges for the child chains. So if we always need to exit, and my money is kind of in a flight because it's in a multisig, how does that exit?
I would say the simplest way to kind of track more complex functionality, and this is suboptimal, but it's kind of a starting point, would be basically to be able to prove the starting state and then to kind of go forward, most likely through an interactive game, to play back up to the kind of like current value state. In the case of a multisig, it's more challenging. I would say basically what you'd want to do is like simplest is where all parties agree on the final state on Ethereum, because then you can just settle it that way. But if they don't all agree, then you have to kind of play an interactive game. Yeah, and it gets fun. And yeah, that sounded a little like state channels in terms of like multi-sigs and interactive games, which is cool. So there's some similarities there. Cool, awesome, I'm done. Thank you so much for listening.